square. At the same time, we know also potential KQ by R. So I think we know everything. So we know for the point charge, what is the field strength, and also what is the potential at a distance R at point P. Then let me differentiate this. dV equal to KQ by R square into dr, or dV by dr is equal to what we get? KQ by R square. What is KQ by R square? It is in fact E, no? Yes. So what is telling? The electric field strength and the potential, they are related by this particular condition. Similarly, we know work done F into dr, work done by electrostatic force. Work done by whom? Work done by an electrostatic force. Work done by electrostatic force, what we write it as equal to minus of du. Why do negative sign? Because work done by electrostatic force should be equal to minus du. Because electrostatic force is a conservative force. And work done by conservative force should be equal to minus of delta. Already you come in work energy chapter, the same similar here. So this should be equal to FF, I can write Q E bar dot dr bar. What is the potential? Can we write in terms of potential? This should be equal to Q into dV. The Q gets eliminated. So integral of minus dV equal to integral of E bar dot dr bar. So let this be point V1, V2, A, B. This is A, B. So this will become VA minus VB is equal to integral of, or VB minus VA, let me write it. That negative sign, let me bring. Okay, there's a one ideal relationship between. So what is this equation? If you know electric field strength, you can bring the potential difference. If you know potential, you can get the electric field. You see the relationship between them. Something very important later in the relation between E and dV by dr, between electric field and potential, we are going to go in detail. Now, timing is what I just brought an idea. If you know the electric field strength, you can bring the potential. If you know electric field, you can get the potential difference. If you know potential in a region, you can get the electric field. Getting the idea, no? So for any charged body, if you know potential, can you get the electric field? Let's differentiate. You'll get the electric field. Or if you know electric field, you integrate, you'll get the potential. Getting the idea? There's some. I just wanted to students to don't accept it blindly, sir. How come you're writing this one? No, we are not writing it blindly here. I just take example of the point charge. From the point charge, what happened? I'll just relate them. So it's not that say so nothing is some blind assumption here. Like that means for every charge body, this is applicable, or only for point charge? No, for every charge body, this is applicable. I don't think that this is applicable for only point charge. Since I took example of point charge, okay, that's all. Then so it's not doesn't mean that only for point charge. It can be applicable for ring, disk, any type of arbitrary charge system. These relationships are valid. Now, one more thing regarding the potential. Potential is defined electric potential is defined only for conservative fields. For non-conservative field, it is meaningless. For non-conservative field, it will be a meaningless quantity. You can write in non-conservative field, but meaningless quantity. So the electric potential is defined only for a conservative field. Okay, there's a one idea. Next one more thing. Suppose if you have a point charge, there are several things I think before going for some application. Let me introduce to all this. So if you have a point charge, so we know these are the field strength, lines of force. Hope you can recollect. Then we have a concentric. So let me draw a there are thin concentric shells. There are thin concentric shells. Okay, look at now. This is a point charge. So what we have kept at center, point charge. Okay, what are these? These circles? No, they are concentric shells. Concentric imaginary shells. So what you're telling is like, shall I call these are equipotential surfaces? Why equipotential? Because due to a point charge, the field will be radially outward. So I'm showing a plain diagram, but basically it's a radial field. So then I'm going to draw a concentric shells of different radii. Then the potential at all points, it will be same. The potential at this point and the potential at this point should be equal. Any reason? Because the both points are at same distance. Similarly, potential at 0.3 and 0.4 should be equal. Similarly, potential at 0.5, 6, 7 should be equal. So what are these thin constant imaginary shells or equipotential surfaces? At all points on that surface, the potential is same. So I'll call that as equipotential. Finish over. then how equipotential surfaces and the electric field strength vector will be always, they'll be perpendicular. Noticing? I'm trying to indicate at several points, not only at few. So the electric field vector will be directed normal to the or perpendicular to the equipotential surface. It's a basic condition. Okay, got the idea. So this is about the electric potential. See, we have started with a certain small definition. Finally, what happened? It is giving us so good information. No? It is so good information it's giving. Suppose say if the electric field is like this, there's a uniform electric field. How the equipotential surfaces here are going to be what are these pink vertical lines? They are the equipotential surfaces here, or lines, you can whatever you can call it. And regarding anything, can we say about their potentials? 1, 2, 3, 4. Definitely, I can say that. V1 greater than V2 greater than V3 greater than. Any reason for that? The electric field vector will be always directed from higher to lower potential. Any reason? Let's come for here. As you move away from the point charge, what will happen to the electric field strength? Will decrease. Potential will decrease. And how electric field vector will be directed from higher to lower potential? Where potential will be more at this point or this point? At point near to the point charge, the potential will be more, no? So therefore the electric field vector will be always directed from higher to lower potential. There's one more important thing. I see so many things. The E bar will be always directed from higher potential region to lower potential region. Getting this one? So these are equipotential lines. Okay, yeah, there's a plane diagram. I'll call this one. What are these? Equipotential lines. So depending upon the different types of field, these particular equipotential lines or surfaces, we can draw it. So now, so finally, what we can suggest here now? Any new unit for electric field can we bring? Volt per meter. Okay, later we'll explore in the E equal to minus dou V by dou X. Okay, let's come for once again. This topic will get repeated. Yeah, similarly here, this is a purpose. I want to find out the work done exagent in moving a test charge from 1 to 2. Okay, what we have, I have a formula like this, no? dV is equal to minus of E bar dot D bar. I want to move it from 1 to 2. Oh, sorry. Let me multiply the charge to it. So I want work done. Okay, we'll do one thing. I want the work done. Work done to move it from 1 to 2. So directly, shall we take help of this one? Integral of V1 to V2 dV by charge. Or Q, or I should multiply the Q. I should multiply with the Q. Because what is the work done? Work done, nothing but potential, you know. So how we define potential? Work done per unit charge. So this should be this one. Directly multiply this with this, we'll get the required answer. Now, if I can find out the potential difference between these 2 points, the problem will be solved. So this should become equal to work done by electrostatic force in moving a charge from 1 to 2 is given by this particular formula. Okay, some technical problem was there. Yeah, let's continue this one. So we have to get this relationship here. What is it? So I'll do one thing. Let me multiply with this Q. So if I multiply here, this will become force, and this will become work done in moving a charge from 1 to 2. I'll write one more step. I wanted to some relationship here. Or let me no. So this will be thing. So what is this quantity? I'll send it to here. Minus of Q dV V1 V2. This should be equal to F into dr 1 to 2. This F into dr is nothing but work done by electrostatic field in moving a charge from 1 to 2. So what is this side? V2 minus V1. Finally, work done by electrostatic field in moving a charge from 1 to 2 should be equal to V1 minus V2. Work done by action agent should be negative of work done by electrostatic force. So therefore, based on this, what we can write it as work done by external agent. This should be equal to Q V2 minus V1. So what is my question? Find the work done by external agent in moving a charge from 1 to